Greetings everybody. This video will give you the background information that you need to better understand our online lab number 5, which investigates something called Hooke's law. Well, okay, what is Hooke's law? Let's look at that first. Well, what happens is Hooke's law is an equation that explains how a mass behaves when it's attached to a spring. And so here we have, and here's the sketch in panel A. Here we have a spring, um, and and here's the mass attached to the spring. Well, in panel A, and we'll assume for now that there's no friction between the block and the horizontal surface. One end of the spring is fixed. The block is attached to the other end. So in panel A, the block is being pulled in the positive X direction. In panel B, so in other words, when the block, let me go back one step, when the block is being pulled in the X direction, well, that's how much the spring stretches. The spring stretches a distance X relative to what's called its equilibrium or unstretched position, also sometimes called the natural length of the spring. That's indicated in panel B. So panel B, again, it's the natural length of the spring, also called the equilibrium position, also called the unstretched or uncompressed state of the spring. So in panel B, the spring is in equilibrium, neither stretched nor compressed. Panel A, the spring is being stretched a distance of X. You know, the block and the spring, because the block's attached to the spring, obviously. It's being pulled to the in the positive X direction, a distance of X. Again, panel B, equilibrium, spring neither stretched nor compressed. Now in panel C, the block and hence is being pushed in the negative X direction by a distance of X relative to what's called the equilibrium position. The equilibrium position is defined as the position when the spring is neither stretched nor compressed. And so in panel A, the spring is being stretched because you're pulling the block a distance of X in the positive X direction. In panel C, the spring is being compressed. You're pushing the block a distance of X in the negative X direction. And so in each case, so panel A, the spring is being stretched a distance of X. In panel C, the spring is being compressed a distance of X. Well, what happens is when in cases A and B, the spring exerts a force on the mass that's attached to it. I call it F. They call it Fs for F of the spring. Well, the spring force, mathematically described by Hooke's law, the spring force is what's called a restoring force, because what happens in case A, when you pull the block in the positive X direction and then you release it, well, the spring force will pull it in the opposite direction. It will pull it in the negative X direction. Equilibrium, panel B, there's no spring force. Panel C, if you compress the block, if you compress the block a distance of X in the negative X direction and then release it, the spring will decompress and push the block in the positive X direction. In other words, when you stretch in panel A or compress as in panel C, whether or not you stretch or compress the spring force always acts in what direction? Towards the equilibrium position, indicated by the dotted line, when the spring is neither stretched nor compressed. So the spring force always acts towards the equilibrium position. If you stretch the spring in positive X, it will pull the mass in the negative X, i.e. towards equilibrium. Panel C, if you compress the block in the negative X and then release it, the spring force will then decompress and push it in the positive X. But notice in each case, F is directed towards the equilibrium position. Well, that's where the minus sign comes from in Hooke's law. F, and well, what is that spring force? Well, F is equal to Kx. We'll get to K in a second. What is X? X is simply the distance that the spring is either stretched, panel A, or compressed, panel C. K is something called the spring constant. Every spring has a unique K value. It is a measure of the stiffness or flexibility of the spring. The larger K value means the stiffer or less flexible the spring is. It's a measure of how stiff a spring is. The larger K value means the spring is stiffer, i.e. less flexible. And the MKS units of K are a Newton per meter. Well, the minus sign simply indicates, in the language of physics, Hooke's law, the spring force is what's called the restoring force. Meaning, notice here, spring is stretched in the positive X, spring force acts in the negative X, in the opposite direction, negative sign. Panel C, spring is compressed in the negative X, and then when you release the mass, the spring force pushes the block in the positive X, well, in other words, opposite. But a more definitive physics explanation is called the restoring force. The spring force always acts, so it's pushing or pulling the object, the mass, towards the equilibrium position. And again, the equilibrium position is indicated in panel B. This dashed line right here, that's when X is 0, so there's no spring force, and that's what we call the equilibrium position of the spring. It is neither stretched nor compressed. And this is Hooke's law. The spring force, i.e. the force in panel A, it's pulling the object back towards the equilibrium, or in panel C, it's pushing the object towards equilibrium. But that force is given by the minus sign again. That simply indicates, notice the difference between A and C. Notice the spring force always acts in the opposite direction of the displacement. Again, displace the spring, i.e. stretch it in the positive X, pulls the mass in the negative X. Compress the spring in the negative X, it pushes the object in the positive X direction. That's the minus sign. But the magnitude is given by K times X, where of course X is the displacement of the spring, whether it's stretched in panel A or compressed in panel C. That's the distance that the spring is either stretched or compressed. In MKS units, that would be in meters. K is the spring constant. Each individual spring has its unique K value. That's what the lab's going to do for us. And the MKS units of K are a Newton per meter. But that's Hooke's law. F is equal to minus Kx. Well, to a very good approximation, and that's Hooke's law. F is equal to minus Kx. And again, what does it apply to? A mass connected to a spring. Now, to a good approximation, Hooke's law is linear in X. So when we plot F versus X, and remember, again, in the language of math and physics, when you plot, one quantity versus another, it's understood F is going to go on the y-axis, and X is going to go on the x-axis. It's y versus X. So when you plot F versus X, because Hooke's law is linear, the slope of the line will equal the spring constant K. Well, how come, Dr. Gomez? Well, let's compare. The equation for a straight line, y equals mx plus b. Hooke's law. Remember, we don't really care about the negative. That just tells us, hey, Dr. Gomez, in the language of physics, it's the spring force is a restoring force. The force is always directs the mass towards the equilibrium position. So y equals mx plus b, F equals kx. Well, notice, see y-axis is F, x-axis is X. Notice M and K. K is going to be the slope of the F versus X curve. Well, we're gonna simulate Hooke's law for two cases. Now, I should mention, let me go back. When we say F is equal to kx, we have just a mass attached to one spring. So F is equal to kx. So what if a mass is attached to, two or more springs? And to keep it relatively straightforward, we'll consider the case of two springs. What if a mass is attached to two springs. Well, Hooke's law still holds. Hooke's law doesn't say the mass can only be connected to one spring. So we're going to look at what if the mass is connected, and this is what we'll do in the simulation. What if the mass is connected to two springs? In this case, the two springs, see in this figure, the purple and the yellow, they're in parallel. Notice the two springs are parallel. Then we're going to look at the case, what if the mass is connected to two springs, which are connected in series? In other words, one spring, the purple spring is connected to the wall, then the other end of the purple spring is connected to the bottom of the yellow spring, which is then connected to the mass. So those two springs are connected in series. In the previous figure, these two springs are connected in parallel. So each spring is connected to the wall, and then each spring is connected to the mass. Well, when we do that, what happens is you have to get what's called the equivalent K value. In other words, how can we somehow treat these springs in parallel as one single spring? And likewise, when we connect the two springs in series, how can we treat these two springs in series as one individual spring? In other words, what we want to get what's called the equivalent K, the equivalent spring constant. Well, for two springs connected in parallel, assuming the purple spring has a spring constant we'll call K1, the yellow spring has a K value we'll call K2. Well, the equivalent spring constant is if you were to somehow combine those two springs into one spring. Well, I guess I close that other file, but the equivalent spring constant I call KEQ. That's simply K1 plus K2. So when we get our data and graph F versus X, the slope of the graph should equal what we get when we just analytically add the two spring constants. And the simulation allows you to choose K1 and K2. Now, when two springs are connected in series, again, purple K1, yellow K2. When they're connected in series, the equivalent spring constant is given by K1 K2 over K1 plus K2. So we're simply going to analytically calculate that value. The simulation allows you to choose K1 and K2. We'll calculate that value in Excel, just type in the equation. Then again, we'll graph the data. And the slope of our F versus X graph should equal the equivalent spring constant. This concept of combining, how can we treat two springs in series as one equivalent spring? How can we treat two springs in parallel as one equivalent spring? That concept will be revisited for those of you who take Physics 11-12 when we combine circuit elements. You can combine resistors in parallel or capacitors in parallel, and you can combine resistors in series and capacitors in series, and you can get what's called an equivalent resistance or an equivalent capacitance. So that concept is nothing new, but basically we're going to compare. For two springs in parallel, the equivalent spring constant is simply K1 plus K2. Enter the formula into Excel, get the analytical value. Then get your data. I'm going to have another video that explains how to run the simulation. Get your data, create your graph. The slope of your graph should equal the analytical, the value you got from K equivalent from the equation. Likewise for parallel. Get your data. First, you choose your K1 and your K2. Calculate K equivalent just by a formula analytically. You type the formula into Excel. Then get your data, graph it. We know it's going to be linear. The slope of that graph should be the same as the analytical value of your K equivalent. All right, let me save this video, and then I'll post another video, running through the whole simulation.